Well, why don't we get started? Okay, so I hope you all had fun finishing up Project 1. We'll be getting around to actually running it, but of course you should already know many of the results because you have the sample programs that we gave you. And just so you aren't disappointed to no longer have any work, Project 2 is now available. You can download it and start taking a look at it. But of course, the first thing that's coming up is the test that comes up on Wednesday. Monday we'll review. Please bring any questions you might have last minute questions. I'm not going to present any set material. I will simply respond to issues or questions that people have. And on Wednesday, there won't be class. There will be instead there will be the test in class. We'll be contacting DSP students who need extra time, and we'll schedule for you folks another. Either you'll be in here for an extra half hour. I don't know if the room is available, but either that or we will put you someplace else. So, as the case may be. All right. So, questions before we begin. Issues. Good. It's time to move into sort of the last unit or so of the course, which has to do with, major unit, the last part of the compiler anyway, which has to do with the execution of the program. And they're actually, if I were to do this, I guess, in an orthodox fashion, or in a fashion that was consistent with what we did before, I'd talk about some specification for what the runtime is supposed to do, but this time I think I'd like to start with a little bit more context. So I don't want to get into a great deal of detail in this lecture, but I'll do the first part of these slides. So at the moment, we have what is basically a decorated tree. This shows up in your projects as inferred types on the various nodes, and also the fact that you have checked to make sure that each object has a proper declaration. Each variable, each identifier has a proper declaration. And at this point, so that's the static semantics of the language. Basically, everything that you can derive from what you can derive as far as correctness and meaning is concerned from the text of the program. And at this point, we get into dynamic semantics. That is, what actually happens, what does it mean, what does the program mean as far as the computation that it denotes? What is that computation? So this involves both the generation of code, the final translation of the decorated information from static semantic analysis into something executable. And also another topic is optimization of this, meaning optimization is the wrong term. It means improvement. What things can we do to improve the execution by taking advantage of special cases and things like this? But first, we have to talk about what our target is. Now, and for this, there's a term that's generally used, virtual machine, to refer to what it is that you are, whatever your code generator generates, what it is that it is targeting, what it is machine code for. So in the extreme case, this is just the instruction set of a piece of hardware, such as RISC-V processor or a Intel x86-64 processor, and that's really the most classical form of compiler, that you are translating from a source language into machine language. Then another alternative is a pure interpreter, in which basically you convert the program into some intermediate, into some other form, some digested form, let's call it, and then a program, an interpreter, goes through and actually executes this thing. Now, this digested program is in the language of some idealized machine, which is what the interpreter is basically simulating. So, and in fact, another possibility is that you translate into another language. You can translate, for example, we could generate C code out of our Python code, and then put that through a C compiler and execute it. So in that case, the C programming language is a machine language. But it could also be a Java. We could also generate Java out of Python and have a Java language. This is something that's done. There are a number of languages in which, in effect, you do that. For example, JetBrains, the people who do IntelliJ, have something called Kotlin, which is actually used in part of the project, although not part you have to deal with. And so that basically uses the same virtual machine as the Java programming language. So we're going to be sticking to, although we're going to stick to hardware, for this project we're going to be sticking to hardware, although in this lecture I'm going to look at something else first. And so the virtual machine consists of hardware, in our case RISC-V architecture, plus certain conventions that you use for writing code. That is, things that are not dictated by the hardware, but you do them. The application programmer's interface, and then some runtime support. In other words, there's a library of things that, for all intents and purposes, you can treat as operations, as basic operations of the machine, but that are actually implemented somehow in a way that you don't necessarily, the compiler writer, do not necessarily have to worry about, unless, of course, you're writing the runtime library. So what are we trying to do? As usual, the first criterion of a good code generator is that it generates correct code. In other words, it generates code that, when executed, does what the semantics of the language say is supposed to happen in response to a given program. So the language says that x plus equals 1 adds 1 to a variable called x, and if the code actually does this, if there's something that you can identify as the variable x that behaves like the variable x, and the code that for x plus equals 1 actually increments that, then you say the thing is correct. Now, that doesn't specify the entire compiler. Nobody would be satisfied with a compiler that merely does what the program says it's supposed to, because there are these other issues. For example, interpreters tend to be considerably slower, by, say, an order of magnitude, than in execution, that is, than a straight compiled program. And sometimes this matters to you. So it may not be acceptable to run at interpreter speeds, depending on what you're doing. Although this is not so big a concern these days, there's an issue of size. So I once was an expert witness in a case where the other side tried to argue that because that program A was not copied from program B because the sizes of the two compiled programs were much different. But of course, that doesn't mean anything. It just meant that they were compiled by different compilers that did different things and could produce programs with two different degrees of verbosity, if you will. Now, these two goals of minimizing size and speed are, in fact, in conflict, just to make life interesting. Or they are often in conflict. Not entirely in conflict, but they can be in conflict. Do any of you remember enough from 61C to guess why that might be? Yeah. Right. So loop unrolling is the phrase. Do they actually use that phrase in 61C, by the way? Do they? Do you know? Does anyone remember? Yeah. Okay. So loop unrolling refers to basically doing a for loop by repeating the code of the for loop. And it can be either you do the entire loop that way, or you can break the thing up into chunks of, say, 5 iterations each, and iterate those a certain number of times. Iterate that block a certain number of times. And the reason that this is good is that by doing so, you make it possible to avoid the instructions that are needed to update the loop variable and so forth. And also you eliminate a bunch of conditional branches and that sort of thing, and that's always tends to speed up the program. But of course, it makes the code much larger. And that, after a certain point, that can be bad because these programs are stored in memory, and you have to, and therefore, if the program gets too big, it overflows this instruction cache, as it's called, and you have to spend a fair amount of time reading more instructions from memory, which is not necessarily a good thing. Now, another consideration is compilation speed. How long does it take to compile things? Now, I've used sort of breadboard compilers that take many minutes to do what a reasonable compiler will do in a few seconds. It is a significant problem when compilation speed is slow, because you're sitting there and you are trying to work, you're trying to debug your program, but every time you make a change, if it takes a long time to effect that change, well, that's not a good thing. That's a load on productivity. And you will even find that there are IDEs that are constantly compiling your program, because as you type, you're adding new text, and they want to constantly make sure that that text is right. So they're constantly checking that, which means constant recompilation as you go. And obviously, if this were slow, it would make for a very unpleasant program editing experience. So these conflicting goals can cause bugs. They cause errors in the compiler. So in particular, when you're trying to make the program fast, you take shortcuts and something goes wrong. And the reason that something goes wrong is that if you're trying to make something fast, then you have to pay attention to the special cases. So for example, a special case might be you are adding a number that you know to be less than 256 to something. And the instruction sequence for doing that might be different from the sequence when you don't know that the number is less than 256. That kind of thing is, so you need to do that. Well, when you have special cases, what used to be a very simple code sequence that was general and would work for everything but was kind of slow in some cases, now becomes a complicated code sequence, which means all that more opportunity for error. So you have to deal with that. So as sub-goals toward these other goals, one might work to minimize the number of instructions that you generate. Another thing that's a biggie is that you choose your data structures carefully. You try to keep the structure of your data static. So in Java, for example, as it turns out, and as I think we'll see, if you ask for field X in an object, the compiler, at the time it produces code, will know exactly where that field is. Either the compiler or, well, actually that isn't quite true. The compiler or the interpreter at the beginning will know exactly where that code is, where that field is. It'll be at some fixed offset, 4, from the beginning of the object, for example. And therefore, the instruction sequence to access it is very simple. It's a load with offset. You say load from this offset from such and such a base pointer. On the other hand, in Python, if you ask for x.f, unless there has been some static analysis or something that tells the Python compiler exactly where, what type of object you're dealing with, that field f will require some kind of a lookup operation at execution time. And the lookup operation not only to get its value, but also even to figure out whether it's even there in this particular case. So that's going to be quite slow relative to Java. Another goal that we might have is to maximize the use of registers, or in general to move things up the memory hierarchy. One of the things that's happened in the last decades is that the speed of processors has become much greater than the speed of memory. So processors can process data much faster than memory can deliver it. I mean, much faster. And in my youth, it was different. You know, the speed at which processor processed things was basically the speed at which memory could deliver them, or maybe slightly faster, but not much. So that's a problem, because it means that your processors have to sit twiddling their thumbs if you're not careful. So what can you do? Well, what you can do is have some memory that is very fast. You can build memory that's very fast. The problem with it is that it takes up real estate on the hardware side. It takes up much more space than the slower memory. It takes up a great deal more energy. And for these reasons, you can have only a limited amount of it. So typically processors will have a few registers, 16, 32, 64, something like this, that are fast, and then they'll have a layer or two of caches that are slower but still faster than main memory, and then they'll have main memory. And then you have secondary memory and the internet and so forth, which are really slow. So so that's execution time. Now, as for compilation, what we try to do is to speed up compilation, is to keep all of our analyses as local as possible, meaning that you don't want the translation that you make for a particular statement to depend on the whole rest of the program, for the simple reason that if you did this in the naive way, you'd be spending quadratic time compiling your programs, which is not going to be very good, especially when you have programs the size of, say, the Windows operating system in the tens of millions of lines. And then the other thing we do is make various simplifying assumptions, conservative simplifying assumptions. So you assume that statements execute in sequence. You assume that procedure calls will always return. Now, when is that not true? Oh, come on. I have a sequence of statements. I execute them in sequence. When don't I execute them in sequence? When is it that I call a procedure and it doesn't return? Yeah? Multi-threaded code. Yeah, you don't have to be that exotic, actually, to come up with examples of this. Yeah. Yes, error handling. So exceptions, for example, can cause the code to interrupt in the middle. And likewise, they can cause a procedure never to return, basically to skip out and go to some error handler surrounding it. So there are a number of instances where this isn't true. You sort of compile in general as if they were true in order to, and then somehow compensate so that you prepare for the faster case. So let's just look at look at the compilation for a particular kind of virtual machine, the Java interpreter, or JVM, Java Virtual Machine, as it's called. So we have a compiler that converts Java programs, .java files, into .class files. You know this. And then, from that point, some Java interpreter or some just-in-time compiler executes the class packages. So far, so good. Now, the interesting thing here about this particular design is that the format, they've gone to the trouble of defining the format of the class file. The Python people also have an intermediate form, but they stubbornly refuse to define what its officially what its format is, and they hold open the option of changing it at any moment. But the Java people made this actually as a book on the form of the Java virtual machine. So these class files are platform independent. I can take a jar file and run it either under Mac OS or Windows or Unix or Linux or whatever you want, and on various operating systems and on various architectures, and it will work in each case. What has happened is that for each of those combinations of architecture and operating system, somebody has gone to the trouble of doing a one-off operation, which is writing an interpreter, a Java interpreter for this, and that's from once you have that, you can run all of these programs. That's the idea. So this particular virtual machine uses a very interesting, a high-level machine language. It looks at a certain level like machine language, like ordinary machine language, but it has features that machines do not in fact have. It recognizes semantics of the programming language that machines generally don't really represent internally. So it functions as a kind of a stack machine. A stack machine is one in which the underlying machinery takes operands off a stack and pushes results on the stack, sort of like the old Hewlett-Packard calculators, where everything is in postfix notation. It can also carry additional information that's used for a number of purposes, among them checking that the file is correct, and also for debugging purposes. So let's just take an example. Let's just look at an example in a little bit of detail. Now let's see. I can probably make one of these things bigger. No, not this one. So on this side we have a. You're not going to move over, huh? Okay. On this side, we have a program. So it's a simple thing that goes through, and it looks at all of the arguments that you've passed in to a Java program, all the command line arguments, and it finds the largest one. So we increment I from 0 up to the length of the argument list, and we do a comparison. We call the compare to method on this string x and the argument, each argument in turn, and whenever the argument is larger, we put that into x. And so we end up with the largest, and then we print that. Now over here on the left, we have the program that this turns into. Well, it's not. It's this is a rendering of the program. The actual class file. Do I have the class file here? Let me see. Probably don't. Well, let's just take a look at it. Just for the heck of it here. I'd like to know what I pressed to make that happen. So if we just do a Java C sample.java. And I look at it, and I look at the class file. This is what you get. Isn't that fun? So these things, like the /312 and so forth, those are octal characters or octal representations of characters. So each one of these is one character, and these guys are this thing that's tilde, whatever this thing is, @ sign. That stands for the null byte. Each one of these things is one byte. And you can see that there are pieces of the program that appear in here, like this stuff. And like this. And then there is a bunch of basically binary junk. So this thing over here, whoops. So this thing over here is a rendering of that in more sort of an assembly language rendering of that, if you will, in some Java assembler format. So the class file contains this information. It says that the name of the class is example. And here we have the various methods and constructors. So there's a constructor, the example constructor, which you notice it isn't actually in this program over here because oh, that's annoying. Because it's a default constructor. So the default constructor has this code. It basically does this, which takes the first argument to the constructor. The first argument to the constructor will be the object that has just been created. the blank object that's just been created. It'll be a pointer to that. So it takes that first argument, it pushes that pointer on the stack. Then it calls a special procedure, namely the constructor for object. So as you remember, that's because every time you execute a Java program, every time you execute the constructor of the Java program, the first thing it does is call the constructor of its supertype. So it invokes special number one, which means the number one here refers to an entry in something called the constant pool, which contains numbers, it contains literal integers and floating point numbers and so forth. It contains strings, and it contains references to fields and methods. That is, these references basically give the name and type of the field and method. So this says invoke the method Java Lang object. It's a constructor which makes it a special method. And so that's what it does. It just calls that. So this is a call. And then we're done, so we return. We have a little extra, and then there's a little extra information down here that says that line 1 of this thing, whatever that is where the instruction 0 occurs. And there is one local variable called this that occupies slot 0 in the virtual machine. So here's the body of code itself down here, the body of this function over here. Maybe I can make this a little bit bigger, I think. So you see that the first thing we do is load the string constant blank, the empty string, into X. So this is again a reference to the constant pool, and this is a reference to a string, namely the empty string. So that gets loaded into, so that constant gets loaded, meaning that it gets pushed on the stack of operands. We then store it. We store the top of the stack of operands into local variable number 1, which presumably is going to turn out to be X. Actually, let's take a look and see if that's true. Local variable table, here we have X, and it's at slot 1. Then we store that, so here's where we store X. And you can also see down here that in this thing that line 5 of the program, which would be 1, 2, 3, 4, 5, this line, is at where we basically get the blank and store it into X. That's at location, machine instruction location 0. That's what this tells us. So here, indeed, is where we do the loading and storing into X. And then it tells us that now here we take the constant 0. So this loads an integer constant, iconst 0, into and it pushes it on the stack. We store that into slot 2, local variable 2, which is I. We then we then load I. We push it on the stack. We take I that we just stored. We put it on the stack. So you can see this code is not very optimized. We take 0 or A's argument 0, which is args, and we take its length. So we push the address of the of args on the stack with a load 0. We then use this operator which takes its length. So this is a machine language that understands the structure and content of arrays, which generally most machines, that's not a typical machine language thing. That's why this is a high-level machine language. Then we do, this would be a standard sort of machine language thing. This is if integer comparison greater than or equal, if the thing on the stack is greater than or equal to whatever. Let's see. Yes. So if it's greater than or equal to the length of the operand I of the operand I, which we just loaded up here, then we branch to location 31, which is down here. So at that point we're done. We're finished with the loop. Otherwise, here we're loading X again. We're loading arguments. We're loading the arguments again. The args pointer. That's a load 0. We load the variable I. That's slot 2. And then we do an AA load means index into an array. And load from so you take the top 2 operands from the stack, which are the array and the index. You index into them, and you take that result and you push it onto the stack. And then we call this virtual method, or that's the instance method, called compare to. And so this is the compare to method in Java lang string. Internally, all of these types are encoded. So this thing here, Java lang string is a method whose type is Java lang string goes to integer, or goes to that's odd. That should be Z for integer, right? So it goes to integer. We then do a comparison, and if the comparison fails, that is, if it's greater than or equal to rather than less than, we go down to 25, which is where and at line 25 we increment variable 2, that is the loop index, by 1, and we go back to line 5. Okay, so that's just to give you a flavor of what this stack machine looks like. It's pushing and popping operands on this stack. And you can imagine what some of these other things mean, like get static, for example. This is where you're getting .out, system.out.println, which is an object, but it's an object it's a static field of the class system. So again, you can see that the amount of information in this particular assembly language is considerably larger than in your standard machine code assembly language that you saw in 61C. And that's just that's part of what gives the Java virtual machine its power. It's actually very interesting. We'll get into this later. This interpreter will take as input class files that have been constructed by the Java compiler or by anything else. And that's a problem because, of course, one of the things you could conceivably do is something nonsensical. For example, you could take you could try to increment the args pointer, the pointer to the array of command line arguments, and you could treat that as an integer and add 1. I mean, in assembly language, you could do things like that. Well, that turns it into a completely nonsensical pointer. So when you load it and try to take its length, you would get nonsense, possibly. And with the way that computer piracy works, if you're good at doing this kind of hacking, you can figure out where you can use that to basically get information you're not supposed to get out of the compiler or out of the execution of the program. So, but it turns out that if you try to feed this file or the equivalent class file into the Java interpreter, this thing called the verifier will say, no, you can't do that. This is not a valid class file. Some of you saw that. I think you probably saw the verifier at work because of a bug in Project 1 for a while, in which it said, in which the thing said that verification failure on some bytes. You may remember, some of you may have encountered that error. I had to do some fiddling to fix that up. And it turns out that was because one of the things that we do in preparing the projects is that we obfuscate the code, which means basically we go in and we mess up the class file in a certain way so as to remove the names of things and make it obscure just what the original code was. And in the process of doing it, this particular program, that it's basically a program that takes in class files and outputs class files, or takes in jar files and outputs jar files. And it got something wrong, or in that particular version, and as a result, produced an invalid class file, which the verifier then caught. So this is done by a form of static semantic analysis, if you will, of the actual generated class file of the assembly language code. And we will, I think I'll take a little time to show how that's done at some later point where we're looking at some of the more advanced topics. All right, so let's just introduce a little bit of terminology. I'm not going to get very far at all today because I can't expect you to really retain the important stuff while you're still worrying about an upcoming test. So let's just look at, we're going to start by looking at procedures as part of the virtual machine environment. And in the usual terminology is that, or a usual terminology is that when I invoke a procedure P, this results in an activation of P, which is actually represented in the machine as what's called an activation record of some kind. And it has a lifetime. So it's there, this information is sitting there in the virtual machine while the procedure is executing and while all the things that it calls are executing. So that we'll call that the lifetime of an activation. Likewise, the lifetime of a variable, or the extent of a variable, is the period of time when there is storage in the virtual machine dedicated to housing that variable. So this is a concept. These are concepts that exist. They're runtime concepts. In other words, it doesn't make any sense to talk about this for a program that's just sitting there as text, because these lifetimes start and end only when the program is actually executing. And Furthermore, you can have multiple activations of the same procedure and multiple instances of the same variable because of recursion and other language features. Now, we're used to most variables disappearing, sort of being associated with some procedure activation and then disappearing when the activation is finished. There's the local variables, but there are other variables that are not so local. Such as, for example, variables that you create by using new, or variables that are declared as static. Now here is a classic, not necessarily up to date, but classic diagram of how a program or how a system might represent the storage, the state of an executing program. You have, if this is the machine's actual memory, you have instructions down here somewhere. That's very simplified. Obviously, there's usually other space that's being used by the operating system. You have static data, meaning data that is that exists for the lifetime of the program, and then only goes away when the program goes away, and is of some fixed size. We'll call this the static data or the data segments, various names like that. Then up here at the top of memory, we have the execution stack, which is related to, for the virtual machine I talked about, it was related to the execution stack there. There's also a stack, you saw it in 61C, there's also a stack that the machine represents in a bare bones machine implementation of something. It grows downward to meet the area where we allocate heap data, that is, data that you get when you say new. Now, of course, you might say, well, the top of memory on my machine, for example, my machine at home, the top of memory is at location 2 to the 36th, I think. Yeah, 2 to the 36th. So that's a lot more memory than, that's how much memory I have. But in fact, the top address is more like 2 to the 64th. So what I'm showing you here is not the physical memory, but the virtual memory of the machine. It's virtual. Everything is, there's always this extra level of indirection. So these things in turn are mapped into the actual physical memory of the machine. And indeed, if this is what things look like to a given process, you remember that they're on a typical Unix application, as you can tell by typing in PS minus E, for example. There's a lot of stuff that's going on. There are a lot of processes, a lot of programs, each of which thinks that this is what memory looks like. And that's all mediated by virtual memory. All right, at this point we're going to stop, and I'll get into the details of this subject probably next Friday. Okay. So, questions or anything like that before we adjourn? Good. I will see you then on Monday. And Monday again is review. No particular material. No new material on Monday.